All right, well, we're now ready to take a look at something else with radicals. I hope you haven't reached your limit. As I've said before, yes, radicals are challenging. We're getting closer to the end. There's actually two more ideas, the last one being the easiest, but we're not there yet. Right now, we're going to talk about radical operations. Now, an operation is, you can see here, adding, subtracting, multiplying, dividing. We actually haven't done quite that skill yet, although, as we've said many times, everything starts to blend together and sometimes overlaps. Let's step back a second. I wonder if you already might know how to add some radicals. Like, what if you wanted to add 2 root 3s of 6 with 5 root 3s of 6? Well, how many root 3s of 6 do you have now? If you have 2 root 3s of 6 plus 5, well, sure, you have 7 root 3s of 6. Pretty easy, right? Well, yeah, that's the general idea because you had like terms. You had like terms. You had what we call like radicals. So when you add or subtract radicals, you must have them be the same. You must have them be like each other. Now, I'm sure you can guess that not every problem is going to be quite as easy as that first one, but they all have that same principle. So if you look at number 1, you quickly realize that nothing really looks the same. Shucks. Well, what we got to do is we got to make them the same. We have to change. We have to simplify, and that's where we start to overlap with some ideas that we've done before. In most cases, it's the larger number that's going to simplify to look a little bit more like the smaller number. So what we want to do is we want to try to pull something out of 54. Now, when you take something out of 54, you want to take out a perfect number. What perfect number is inside of 54? Well, it's 27. That's because 27 has a perfect root. Of course, when it comes out, it's going to turn into a 3. Now, we also want to try to take out some of this a. In fact, you want to take out the most amount of a that's going to divide with this 3. And you should be thinking of taking out a3. Of course, you also have an a1 that's left behind. So when I take out this a3, it divides to just be a. Now, what's left behind? Well, that's actually what might be more important, because what's left behind is what is supposed to look the same as what I started with. So these numbers I circled in black, they are left behind, but what I want you to notice is that is exactly the same as the other term that I started with. That's good. That means that we're going to be able to solve this problem, because now we have 6a root 3s of 2a, and we want to add 3a to them. So if I have 6a and I want to add 3a, and of course, as we already said, the radicals are the same, well, now it's a pretty easy problem. Now I can say that I have 9a of those radicals. Of those third roots of 2a. So see what we did? We made the larger radical look like the smaller one. Okay, now in a case like this, both of these can be simplified because both of these are able to have some perfect square roots inside. So we got to get to the business of taking or splitting up each of these items. Maybe some of this you can do in your head. Maybe you're thinking of splitting up 20 to be 4 times 5. Now, if you're not sure why I'm doing that, 4 is a perfect number because, again, this is a square root problem. So the 4 is the one that's going to come out. It does come out as a 2, but it leaves behind that 5. Well, we can also take some of this x out. In fact, we want to take out the most amount of x that is divisible by 2. And you should be thinking of splitting that or taking out an x squared, but you leave behind the x. So we take out the x squared. Remember, when you take it out, it divides. It divides by the 2, and that's why we end up with just x to the first power. It does leave behind an x. Over here, same kind of business. We want to try to split up 45. We want to try to break out some of this x. How's the splitting up of 45 going? We've done this many times now. You want to find a perfect number inside of 45. It's a perfect square number. Perfect square number. Remember, your squares are 1, 4, 9, 16. Well, 9 is the perfect number that's inside of 45. Okay, but you have to think of it as 9 times 5. The 9 is going to come out. It comes out as a 3 because you take its square root. It leaves behind the 5. We already split this x up in the previous problem, so the same thing. You're going to be able to take out 2 of those x's. When you take that x2 out, it does divide. That's why we end up with just x to the first. But it leaves behind an x. Well, these root 5x's are the same. That means that we're allowed to do the addition problem. So we add the 2x and the 3x, and that leaves us with 5x, but the square root of 5x is left behind underneath. You ready to try this problem on your own? This would be a perfect time to pause the video, and when you come back, I'll work it out with you. All right, so yes, you want to be splitting up 24. The reason that we want to do that is because there's a perfect number inside of 24. It would be the number 8. The 8 is able to do a cube root, and it's able to come out as a 2. It does leave behind the 3, and that x was not big enough to come out. Now you want to try to find a perfect number inside of 81. It's a perfect cube number. It's not 9. Okay, 9 is not a cube number. It's actually the number 27. Okay, now 27 times 3 equals 81, but 27 is a perfect cube number that comes out as a 3. It does leave behind a 3, and that x, well, that never changed. Are you getting the hang of it? You always want these roots or radicals to be the same. The radicals are the same, although I forgot to write the little 3, but they still are cube roots of 3x, so I can subtract 2 minus 3. That leaves me with a negative 1, or just a negative cube root of 3x. All right, so that's adding and subtracting. What about if we want to multiply and divide? Well, the good news with multiplying and dividing is you don't need to make anything the same. You just need to have the same. You have to have the same index. Now, I haven't actually used the word index yet, but the index is just that little number that we've been calling the root. Same thing. Just wanted to give you that vocabulary. We can call that number the index. So it just needs to have the same index. And if it does, you're going to say that these are a little bit easier because since we obviously have a root or an index of 4, I can just jump right in here and I can multiply. Now, what do I multiply? Well, the numbers out front are called the coefficients, and we've actually always multiplied coefficients in this class. But it turns out that you can now multiply the part that's under the radical. Now, in this case, I'm multiplying an x to the third times an x. Remember that you want to add the exponent, so I end up with x to the fourth. Pretty nice. You just multiply. But you do always want to be aware that there might be additional steps. In this case, it is the case that this index of 4 and this power of 4, they're going to cancel because we can really take out this x to the fourth fully. And when we take it out, it's going to divide. And of course, when it divides, we end up with an exponent of 1. So we get 10x to the first, or just 10x. How about number 4 over here? Nice example of doing the distributive property. Sure, you can do the distributive property. That's the same as multiplying. And oh, by the way, the indexes are all the same here. They're all square roots. We don't have to write that. But since they're all the same, we can multiply. Now, when we multiply, underneath 2 times 32, of course, is 64. And x times x is x squared. Remember, you add the exponents. And when I multiply the 9 with the 2x, I'll get 18x. Can you simplify any more? Are you able to take something out? Well, actually, 64 is already a perfect square, so it entirely comes out as 8. And x squared, of course, that's a perfect square, so it entirely comes out as an x. No more square roots, since both of those were perfect to begin with. Now, when you look at this 18, you want to be thinking about splitting it into a 9 and a 2, because, of course, 9 is your perfect number that's able to come out. So we're going to get a, remember, when 9 comes out, we have to do its square root. So you'll get the number 3. But it does leave behind a 2, and it leaves behind an x. Okay, so again, I split up 18 into 9 times 2. I pull out the 9, but whenever you take out a number, it always gets smaller, and again, it turns into its root, which is 3. Ready to try one on your own? It's a division problem. So instead of multiplying the numbers underneath, why don't you divide the numbers? Okay, I'll show you how to do it, but I encourage you to think about dividing the numbers to get started. All right, now of course the index is the same, which allows us to do this in the first place, but if I divide 54 and 3, when I divide them, I'm going to end up with 18. Now, when you divide the x's, what you're really doing there is you're subtracting those exponents, so we end up with x to the 7th. Now, can we split this up? Can we break this down anymore? Well, I don't know. Are there any perfect numbers inside of 18? Okay, got to be careful. Don't tell me that there's a 9 inside of 18. Okay, that is not a perfect cube root. Okay, remember, your perfect cube roots are numbers that come from cubing, like 8, like 27, like 64. Okay, so none of those numbers are inside of 18. Can't pull anything out of that. But there are some x's you can take out. Remember, you want to take out the highest amount of x that's divisible by this 3. The highest amount of x that's divisible by this 3 would be x to the 6. Now, I still have an x that's left behind, but I can take out this x to the 6 by dividing it by 3, and that gives me an x squared. Honestly, nothing else came out. Everything else stays underneath. So we end up with what would be called the x squared times the cube root of 18x. Now, there are some problems that quite simply we would say are a little more advanced. They're a little more advanced because we don't have the same index, but we will be able to do some special thinking to get the same index. And that special thinking would be that we're going to switch to a rational exponent. I should have had you write that. We're going to switch to a rational exponent to create the same index. Let me show you what I mean. If you look at the cube root of 2 times root 3, please do not just do something silly like multiply and somehow get some kind of 6. You don't have the same index. You're not allowed to multiply. So what I can do is I can think of this cube root of 2 as 2 to the 1/3 power. Okay, because remember, a root is the same as a denominator. Well, I can do the same thing with the 3, but I would have to think of that to the 1/2 power. Okay, because remember, a square root is assumed to have an index of 2. Now, you still don't want to do something silly like try to multiply 2 times 3. You still don't get 6. But what I can do is if I make these rational exponents, have the same denominator, there will be something we'll be able to simplify. So 1/3 and 1/2, can I make them the same denominator? Well, I can if I think of them as a denominator of 6. Now, can I just make it a denominator of 6? Well, I'd have to multiply the numerator by 2. So 2/6 is the same as 1/3. And can I just make this a denominator of 6? Yes, if I multiply the numerator by 3. So I'm changing both of my exponents to have the same denominator. Now, when I change them to have the same denominator, it turns out that what I've really done is I've changed them to have the same index, to have the same root. Let me show you, because we're able to write 2 to the 2/6 power as the 6th root of 2 squared. Okay, because we can write it, we can switch it back to radical form. Can we do the same thing here? Sure. We can write this as 3 to the 3rd power with a 6th root. So notice that we're changing back to radical form because now we have the same index. Now, by the way, the 2 squared is the same as 4, and of course 3 cubed is the same as 27. I'm doing a little bit of math because ultimately now I have permission to be able to multiply under these radicals. I can multiply 4 27s and end up with 108. A little tricky, a little fancy, but it takes knowing that if I can make these exponents have the same denominator, that I will eventually be able to think of them as having the same index. How about this problem? Yes, this is the square root of the cube root of 2. Okay, now as I said, we can write this with exponents. Okay, now if I want to write this with exponents, I can think of the cube root of 2 as being 1 over 3. I can think of the square root as being 1 over 2. And so what I'm really doing here is I'm creating two exponents that now you can multiply. And if you multiply them, you multiply the numerators to be 1 and the denominators to be 6, which is going to simplify to be the 6th root of 2. Ready to try one? Okay, now again, as you look at this, the roots, the indexes are different, but you can start the problem by writing this in rational form. So I want to write this as a 1/3. I want to write this as a 1/4. I just want to make sure that you see that it's the entire 2y that is to the 1/4. See if you can take it from there. You want to continue to change those fractions to look more the same. They have to have the same denominator. Now the denominator that you want to make would be 12. Can I just make a denominator of 12? Well, as long as you multiply the numerator by 4. And can I just make a denominator of 12 on the other one? Well, as long as you multiply the numerator by 3. Okay, now, at the time that I have this as 4/12 and 3/12, I can switch back to radical form. When you switch back to radical form, remember the numerator is the power and the denominator is the root. So I'm going to have a root of 12. Carefully notice here that my exponent of 3 applies to the entire 2y. Now, the last thing I need to do here is understand this exponent goes to both of these, and understand that you are now allowed to get underneath here and put everything together. 2 to the 3rd power, this blue 2 to the 3rd power, that is going to be 8. The y's are going to add together, y to the 4th, y to the 3rd. We're going to add those up. We're going to end up with 7. Now, there's nothing else to do here because 12 is too big of a root. I can't pull any numbers out since 12 is already larger than y to the 7th, and there's no perfect number inside of 8. All right, so how about this problem on the back? If you flip it over, if you scroll to the next page, you see what appears to be like a big bomb. Just a little bit jokingly, yeah, it's more of a challenging problem. I don't want to say it's a bonus problem. It's just a problem that when you're ready to think about it, you'll find out that it uses all the same ideas from the front, of course, just very carefully, because what we're actually doing here is we're squaring a binomial. Now, to square a binomial is to actually multiply it by itself. So the first thing I want to do here is I want to understand that I'm going to have to do the FOIL method. If you thought that maybe we were just going to bring this exponent in, as we've joked many times, that's a math teacher's nightmare. Even if I'm not with you, let's try to stay away from nightmares. So to square this is to actually multiply it by itself, which is setting us up for the FOIL method. Can we do the FOIL method? Well, it's just a multiplication problem. So you're going to multiply 5 root 2 times 5 root 2. That means you can multiply the 5s to be 25. Now, when you multiply the root 2s, you're allowed to multiply underneath, and that gives you a root 4. So you can multiply the 2s to be 4. How about multiplying 5 root 2 times this minus 4 root 3? Again, you can multiply the 5 and the minus 4. That'll give you minus 20. You can multiply underneath, and that'll give you a root 6. It turns out that negative 4 root 3 times 5 root 2 is actually going to be the same outcome. It's going to be another minus 20 root 6. And then our last one would be multiplying, it turns out, negative 4 root 3 times negative 4 root 3. Now you can multiply the negative 4s to be positive 16. And yep, you're allowed to multiply underneath to get a 9. It's actually the square root of 9. Now, there's some math that can be done. You should recognize that the square root of 4 is actually the same as 2. So now I have 25 times 2. That's actually known as the number 50. You have some math happening right here. The square root of 9 is actually the number 3. So now I have 16 times 3, which is actually known as the number 48. And then these negative 20s, root 6s, they are like each other. So now you have negative 40 root 6s. Okay, and the only thing left to do would be to actually add like terms. In this case, my like terms are just good old numbers, thank goodness, and those add up to be 98. So we get 98 minus 40, the square root of 6. Now, just like we've done in other days, here's some homework problems to practice. I will provide an explanation video. I encourage you to try the homework first, watch the video second, and we will keep learning until we get to the point that we're ready to take more of a grade on this skill.